All right, let's dive right into the heart of quantum computing. Today, we're talking about the fundamental building blocks that make the whole thing work, quantum gates.
So to really get our heads around this, let's start with a super simple comparison. You know how a normal computer bit works, right? It's just like a light switch. It's either on, a 1, or it's off, a 0. That's it. But a quantum bit, a qubit, well, that's a whole different ballgame. Think of it more like a dimmer switch. It can be all the way on, all the way off, or, and this is the key part, it can be in this whole spectrum of possibilities in between.
And that whole dimmer switch idea? It's actually the perfect jumping-off point. Because to really understand quantum gates, you first have to appreciate the totally weird and incredibly powerful thing they're designed to control.
And that thing is the qubit. It's the basic unit of all quantum information. And this is where your brain might start to melt a little. Because of a property called superposition, a qubit can be a 0, it can be a 1, or it can be both at the exact same time. Yeah, you heard that right. And it's this mind-bending ability that gives quantum computing its unbelievable potential.
Okay, so this brings up a pretty big question, doesn't it? If we have these amazing new actors on the stage, these qubits, how in the world do we actually tell them what to do? How do we direct the play and get them to perform the calculation we want?
Well, that brings us to the quantum rulebook. The answer to directing our qubits is a very specific set of instructions or operations that we call quantum gates.
So what exactly is a quantum gate? It's basically just a fundamental operation you perform on a qubit. If you've ever looked at how a regular computer works, you can think of it just like a logic gate, an AND or NOT gate. They are the absolute rock-bottom building blocks you use to put together a quantum program.
But, and this is a huge but, there's a critical difference here that gets to the very core of how quantum mechanics works. While classical gates can be a one-way street where you can lose information, quantum gates are always reversible. You have to be able to run the operation backward and get your original state back perfectly. In the quantum world, information is never really lost. It's a fundamental rule of the universe.
All right, so what do these operations actually do? Let's take a quick tour of some of the most important gates you'll find in any quantum programmer's toolbox.
First up, we have the solo acts. These are the single qubit gates. And just like the name says, they operate on just one single qubit at a time to tweak or change its state.
Now, a couple really famous ones are the Hadamard gate, which is kind of like the magic wand that creates superposition in the first place. It takes a plain old 0 or 1 and puts it into that both at once state. Then you've got the Pauli gates. The most common one is the X gate, and it's basically the quantum version of a classical NOT gate. It just flips a 0 to a 1 and a 1 back to a 0. These are the absolute essentials for manipulating a qubit.
But let's be honest, the real power isn't just what one qubit can do on its own. It's what they can do when they work together. And that brings us to the team plays, multi-qubit gates.
The absolute star of the show here is the C-NOT gate, which stands for controlled NOT. You can just think of it as an if-then command. It takes two qubits, a control and a target. And the rule is simple. If the control qubit is in the 1 state, then it flips the target qubit. If not, it does nothing. This simple bit of conditional logic is one of the most powerful tools we have, because this is how we create entanglement, that bizarre, spooky connection where the states of two qubits become linked no matter how far apart they are.
Okay, so we've got our single qubit gates and our multi-qubit gates. We've got our building blocks. Now, how do we actually put them together to do something useful?
Well, it's actually pretty simple. We just string these gates together, one after another, in a specific order. And that sequence of gates has a name. It's called a quantum circuit. You can think of it like a recipe, where each gate is a step in the instructions. Or maybe like a musical score that tells each qubit exactly when and how to perform.
And really, almost any quantum algorithm you can think of follows this basic dance. First, you get your qubits ready, usually in a simple starting state. Then you apply a carefully designed series of single qubit gates like the Hadamard and multi-qubit gates like the CNOT. And finally, when the dance is over, you measure the qubits to read out your final answer. So what can these circuits actually do? Well, this is where it gets really exciting. A circuit running something called Shor's algorithm could, in theory, factor huge numbers, which would break most of the encryption we use today. Grover's algorithm can search through massive, unsorted databases at speeds a classical computer couldn't even dream of. And we can use them to simulate complex molecules, to discover new medicines and materials. It's incredible stuff.
So for this last part, let's connect all this theory to the real world. I mean, it's great to talk about these gates, but how do we actually build them?
What do they even look like?
Because these quantum gates aren't just equations on a blackboard, they are real physical things that happen. For example, in a quantum computer that uses superconducting circuits, a gate is actually a very carefully shaped microwave pulse zapped at the qubit. For a trapped ion computer, it's a laser beam that's aimed with mind-boggling precision. The physical hardware is just as wild as the quantum theory itself.
So if you take away just one thing, it should be this. Quantum gates are the engine of this entire revolution. They are the essential piece of the puzzle, the mechanism that lets us grab the weird, counterintuitive rules of quantum mechanics and turn them into actual, tangible, world-changing computational power.
When you really stop and think about it, these gates give us a completely new language. It's a language that lets us speak to the universe on its own terms, using its own rules. It's a way to ask questions we've never been able to ask before. So the only real question left is, what will we ask it first?